Kinesthetic feedback enhances overall VR user experience as it provides realistic tactile cues involving virtual objects. However, to provide sufficient force feedback, current devices need complex and bulky components, which can cause severe fatigue from users. To tackle this disadvantage, researchers provided haptic illusions with smaller size and simple hardware setup. Likewise, we use finger tendon vibration to create illusory sensation of extension and flexion with simple hardware configuration. As we apply this idea for interaction scenarios, we use short-duration finger tendon vibration to implement kinesthetic haptic cues. Our contributions are the following: a novel idea of using short-duration finger tendon vibration to implement kinesthetic haptic cues for virtual object interactions with associated motion illusions. Perception studies to assess whether short-duration finger tendon vibration of less than 5 seconds provides sufficient illusions for real-time haptic feedback during immersive virtual object interaction. Example use case scenarios demonstrating the use of finger tendon vibration-induced finger motion illusions to promote realistic and immersive haptic experiences for virtual object interactions, with a practical interaction guideline for finger tendon vibration haptic rendering methods. Lastly, an evaluation for VR object interactions, showing that finger tendon vibration is an effective method to increase overall VR experience. To create finger flexion and extension sensation, we developed a simple wearable haptic interface that applies tendon vibration in real time. This device places 2 ERM motors on the proximal planax of the index finger, one on the dorsal side and the another one on the palmar side. Vibrating the dorsal side results in a perceived flexion illusion, while the palmar side results in a perceived extension movement. With our haptic interface, we first conducted a study to measure the minimum duration threshold for creating the illusion. In result, 0.75 seconds turned out as a sufficient minimum duration for finger tendon vibration illusion, and we set this value as our minimum threshold estimate for the future use. Subsequently, we conducted 2 perception studies. First, we measured how finger tendon vibration affects the perceived pinching force. Participants held a pressure sensor to measure their pinching force, then conducted a training session to memorize the force to reach 5 newtons. Then they performed the same pinching force without seeing the raw force data. While performing, we vibrated their left index finger, expecting a significant force difference between 2 hands due to finger tendon vibration illusion. However, there was no significant difference in relative force changes, so we conclude that short duration, less than 5 seconds, does not have a significant effect on perceived pinching force. Next, we measure how finger tendon vibration affects the perceived finger movement. In the study, the participants self-reported the perceived movement by physically moving their index finger after the finger tendon vibration illusion. We measured the finger movement by using 8 motion capture cameras around the finger. In result, we found that participants felt a clear distinction with perceived finger movement. Furthermore, the perceived movement increased as the vibration duration became longer. Using these results, we derived 6 different interactive VR scenes using finger tendon vibration that cover diverse aspects of VR object interactions, from 3 UI components, which involve simpler interactions, including button, scroll bar, and rectangle, and 3 3D objects which represent physical properties such as train, ball, and kettlebell. We also came up with 4 detailed rendering methods for finger tendon vibration's trigger and duration time. We evaluated these rendering methods to our VR scenes and examined in which scenarios certain finger tendon vibration rendering are more effective than others. We recruited 16 participants and measured body ownership and tactile sensations using the Avatar Embodiment Questionnaire. We also added 3 more questionnaires related to realism, immersion, and enjoyment for the virtual object scenarios. In result, both trigger methods performed similarly without much difference. This denotes that for interactions long enough, the illusion onset delay is negligible. For duration methods, full perform better than fixed, especially in scenarios where the participant expect a constant force. This highlights the significance of longer vibrational tactile cues for scenarios with constant force. Lastly, we compare finger tendon vibration with simple vibration and no vibration. Using the same VR scenarios and questionnaire, we observed that finger tendon vibration significantly improves VR experience, especially for body ownership. In particular, finger tendon vibration was effective in providing users a sense of resistance on their finger, which the other 2 vibration settings could not. Compiling these results of our perception studies, rendering method evaluation, and VR experience evaluation, we outlined a design guideline to utilize finger tendon vibration and use illusions for immersive virtual object interaction. In this paper, we explored the novel use of finger tendon vibration for immersive VR object interaction. We found several perceptive qualities of short-duration finger tendon vibration through our perception studies, and organized effective exemplary VR scenarios and rendering methods. Lastly, we showed how finger tendon vibration is effective in improving the overall VR experience. We hope these findings promote finger tendon vibration's application in VR, providing users with high-quality immersive VR experiences.